Today's topic is nuclear chemistry. Our learning targets include being able to distinguish between alpha, beta, and gamma radiation. And if you're in an honors class, you'll also be responsible for understanding what a positron is and electron capture. We are also going to be looking at writing balanced nuclear equations. So recall nuclear notation. This symbol, X, represents the symbol of an element. A represents the mass number of an element, and Z represents the atomic number. We are going to be using standard nuclear notation for isotopes as we write nuclear equations. Let's take a look at the picture on the left versus the picture on the right. Go ahead and get your periodic table out and see if you can identify what element is pictured on the left. Hopefully you are identifying it as an atom of helium. So we know it's helium because inside the nucleus, we have 2 protons and 2 neutrons pictured. We know it's a neutral helium atom because these blue dots represent the electrons on the outermost energy level. So it doesn't really matter what color the protons and neutrons are because they're identical in number. So we know that the yellow and the orange are distinctly different. So we can identify one color as the proton, one color as the neutron. Now, we know it's a neutral atom because the number of electrons is equal to the number of protons. On the right side, we have the same subatomic particles, 2 of each particle. The only difference is that instead of being in an intact helium atom, they are separated. So when we're examining these 2 pictures, it's important to understand that there is a difference in their masses. We call that difference the mass defect. So let's take a look at the data. On the left, the mass of the helium atom, as it's intact, is 4.00260 atomic mass units. On the right, when the subatomic particles are separated, the mass of each particle separated and then added together is 4.03298 atomic mass units. So you can see that there is a distinct difference between those numbers. The question that comes up for people then is why? Why is there a difference? Well, it has to do with something we call the binding energy. The binding energy is the energy that must be added to the nucleus in order to break it into separated protons and neutrons, into separated subatomic particles. And the difference in mass then is caused by the release or the absorption of that binding energy. Nuclear binding energy is important to understand the value of because it gives us an idea of the stability of the nucleus. So when this value, the nuclear binding energy, E, in the E equals mc squared equation, is high in number, that indicates that we have a stable nucleus. So what's important for our purposes in this class is not to calculate the binding energy, but to understand what it signifies, and that is the stability of the nucleus. So in this famous equation, E represents energy, more specifically binding energy, M represents the mass defect that's measured in kilograms, and C is a constant. It is the speed of light, and it's 3.00 times 10 to the 8 meters per second. When a nucleus is formed from nucleons, the binding energy is released from the nucleus. Let's take a look at a graph depicting nuclear binding energy versus the mass number. So on the x-axis, we have the mass number increasing from left to right. And on the y-axis, we have the binding energy per nucleon. So notice that as we initially begin from the hydrogen atom and keep adding protons and neutrons and work our way up from hydrogen to helium to a larger isotope of hydrogen to lithium, lithium-6, and then lithium-7. You get lithium-7 by adding a neutron. Notice how there's a steep incline in the binding energy as we begin adding protons and neutrons to very small nuclei. As we continue to increase, that rise in nuclear binding energy eventually tapers off. It stops around iron 56. Iron 56 is considered to be the most stable nucleus because as soon as we move past iron 56, you can see that the slope of the graph begins to decline, showing a decrease in stability due to a decrease in binding energy. This trend indicates that the nuclei of intermediate mass numbers, like iron 56, sulfur 34, these intermediate mass numbers are more tightly bound and therefore more stable than those with either much larger mass numbers or much smaller mass numbers. Now, when we are considering the processes of fission and fusion, remember fission is when heavy nuclei gain stability by splitting into two mid-sized nuclei, and in doing so they give off energy. Fusion is the combining of nuclei to form a larger nucleus. That process also releases energy. So depending on the size of your nucleus, that's a good indicator of whether the nucleus will undergo fission or fusion. So the trend is the larger the nucleus, the more likely it is to split or to undergo fission, and the smaller the nucleus, the more likely it is to undergo fusion. Both of those processes release significant amounts of energy. Now let's look at specific types of radiation, starting with the alpha particle. The alpha particle is symbolized using the helium symbol with a mass number of 4. Remember, this number represents the mass number for an isotope, and the bottom number represents the atomic number or the number of protons for that isotope. The alpha particle can also be represented as the symbol alpha. Alpha is a Greek letter, so this little fish-looking letter looks like a fish. That's the alpha particle, or that's the alpha symbol, and you can see the mass number and the atomic number at the bottom are the same. So we also call the alpha particle a helium-4 nucleus. And usually alpha particles are emitted by heavier nuclei with atomic number. Remember, Z represents the atomic number, with atomic number greater or equal to 84. Now, even though their ionization power is very high and they can cause a lot of damage, alpha particles, because of their large size, comparative large size to other types of radiation, have the lowest penetrating power. Next, we're going to look at the beta particle. The beta particle has an E, a lowercase e, with a mass number of 0 and an atomic number of -1. So this is also depicted as the Greek letter beta with the same mass number and charge as an electron. The beta particle, just like the alpha particle, is emitted by nuclei. But a beta particle is emitted by a nucleus with too many neutrons. So when there's an excess number of neutrons, typically that nucleus will undergo a beta decay or beta emission to reduce the number of neutrons present. This process usually occurs in nuclei that have a ratio of 1.5 neutrons or higher to 1 proton. The penetration power of a beta particle is greater than that of an alpha particle because of its small size. Next, we have the gamma ray. So the gamma ray, notice the name, it's a ray. It is pure energy. So it's not called a particle because it's a high energy photon. The gamma ray has no mass and no charge, and it frequently accompanies other forms of nuclear decay. So for example, if a radioactive nucleus is undergoing alpha emission at the same time, it could also be releasing a gamma ray. The penetration power of a gamma ray is the greatest because, again, it has no mass. So that's why there's a 0 up here, no mass and no charge. So it's pure energy, no charge. Some additional types of radiation, if you're in an honors chemistry course, that you're going to be required to know are the positron. So the positron, if you look at the symbol, is very similar to a beta particle. It's also depicted using the same Greek letter as the beta particle, but you'll notice that even though the mass is similar to that of an electron, it has an opposite charge. So the positron, positive, right, has a positive charge. And a positron is emitted by nuclei with too many protons. And because it has no mass, its penetration power is similar to that of the beta particle. Lastly, we have the electron capture. So electron capture, notice the symbol is the same as the beta particle because it is in fact an electron. The electron that is captured by the nucleus comes from the electron cloud or the inner orbital. So part of the cloud that the nucleus is closest to, that's where the electron can be captured from by the nucleus, and the electron is then consumed. So it's not actually emitted the way a positron can be emitted, or a beta particle, or a gamma ray, or an alpha particle can be emitted. Electron capture is when the electron is consumed by the nucleus. So just some additional information about these two particles. They both have the effect of converting a proton into a neutron. So when there's an excess of protons in the nucleus, these are two types of nuclear reactions that are likely to occur. Either a positron will be emitted or there will be an electron capture. And because they both have no mass, they have the same penetration power as a beta particle. So let's actually look at what I mean by penetration power. We're talking about what can block these types of radiation. So let's start by looking at the alpha particle. Notice, first of all, the alpha particle is depicted with two positively charged green spheres and then two white spheres with no markings on them. So remember, the alpha particle is a helium nucleus, and the mass number is 4, so that's why we've got 4 subatomic particles clustered together, and the number of protons is 2. So please remember, the alpha particle is actually positively charged. It's got a +2 charge because of these 2 protons that make up part of that particle. The alpha particle is large. It's the largest form of radiation, and it can be blocked using something like paper or skin or some types of clothing can block it as well. If the alpha particle comes into contact with your skin, please understand that it will cause damage. It is the most ionizing form of radiation. If it somehow gets into your body, it will also cause significant damage. But because it is a large particle, it can be blocked by something like paper and the dead skin layers that make up your epidermis, the surface of your skin, will also block it from getting further into your body. The beta particle needs something a little bit more dense, some more dense material to block it. So what we would need is something like a metal foil, something like aluminum foil, copper foil, tin foil, any kind of metal foil a couple millimeters thick will effectively block a beta particle. Neutrons, we're going to come back to this, but neutrons are involved in fission reactions. A neutron is needed to collide with a larger nucleus, a radioactive nucleus, to cause it to split and then cause that chain reaction through other neutrons being released and then colliding with the large nuclei. They are very fast-moving particles, and they are used in nuclear reactors and fission reactors. What is needed to control their speed and to slow them down and stop them from moving so fast is hydrogen-rich medium such as water. Okay, gamma ray is the other type of radiation that we want to focus on. A gamma ray, remember, has no mass and no charge. It has the greatest penetrating power because it is the smallest. It has no mass or no charge. So several feet of concrete can block a gamma ray. And also, if you have some kind of dense metal that's several centimeters thick, like lead, that can block the gamma ray as well. So think about when you go to the dentist and you get a dental x-ray, they usually put an apron on your body so that the rest of your vital organs don't absorb that radiation coming from the x-ray machine. Now we're going to take a moment to write some nuclear equations. So we're going to start by looking at alpha decay. One thing you want to make sure is in these equations, you want to make sure that both sides of the equation, both sides of the arrow, so this is the arrow right here, it represents an equal sign, okay? So whatever's on either side of the arrow, the numbers need to be equal. To solve for the missing variables a and z, we need to use some simple algebra. So if you were to set up to solve for a, 238 equals a plus 4. You were working with the numbers up at the top first. So if you solve for a by subtracting 4 from both sides, a then equals 234. So that's what this number is at the top. That's the mass number of this isotope. The bottom number, then, z, is the next thing you would solve for. So 92 equals z plus 2. So to solve for z, subtract 2 from both sides, and then z equals 90. So this bottom number here is 90, which represents the atomic number. And we would use 90, the atomic number, to look up the identity of this isotope. Now let's actually break apart the components of this equation to identify what each of these isotopes is going to be called. Uranium-238, the first isotope, we call that the parent nuclide or the parent isotope. So what's happening in this equation is that uranium-238 is undergoing alpha decay or alpha emission, and it's going to release an alpha particle in that process. So the alpha particle, remember, is the helium nucleus. So I showed you how to solve for A and Z, and remember Z was 90. So we would use 90 as the number we would look up on the periodic table, the atomic number, and note that 90 is thorium. So the daughter nuclide, which is X, the more stable product after the alpha particle is emitted, then is thorium-234. This equation represents a beta emission or beta decay. We're looking at iodine-131. That is going to be our parent nuclide or our parent isotope. The beta particle, represented by E, the symbol for an electron, with a mass of 0 and a charge of -1, is going to be emitted from the iodine-131 isotope. So in order to identify the daughter nuclide, we would need to solve for A and Z as we did earlier. So let's set up our equation. 131 equals A plus 0. That's the top row. Solve for A. Hopefully you can see that's pretty simple. It's just A equals 131. Okay. Now we're going to look at Z. So we have 53 equals Z minus 1. So solve for Z. Add 1 to both sides. Z equals 54. So we would use 54 to look up the identity of our daughter nuclide on the periodic table, 54 being the atomic number. So take a moment to look that up. Hopefully you were able to identify the daughter nuclide as xenon 131. Now let's take a look at a gamma ray emission. So our parent nuclide in this case is radium-226. Notice the way the words and the hyphenated number are written below the symbol. That is name of the isotope. So radium-226 is undergoing not only a gamma ray emission, but it's also releasing an alpha particle. Remember that gamma radiation usually accompanies other radioactive emission because it represents energy that's lost when the nucleons in a nuclear reaction reorganize themselves into a more stable arrangement. So because a gamma ray is pure energy, it has no mass and no charge, it won't actually affect the calculation of A and Z. So we're going to still calculate the values of A and Z to obtain the identity of our daughter nuclide. So starting with the numbers at the top, 226 equals A plus 4. The 4 comes from the alpha particle. So solving for A, subtract 4 from both sides, and you get A equals 222. So that represents our mass number. Now let's solve for Z. The bottom number on radium, the atomic number, is 88. 88 equals Z plus 2. Subtract 2 from both sides. Z equals 86. So we're going to use 86 to look up the identity of our element on the periodic table. Were you able to identify the daughter nuclide as radon-222? Hopefully you got that right. Now let's try to write nuclear equations from scratch. So let's start with copper-62. Copper symbol is Cu. The mass number is 62. That's going to go up at the top. And then you'll need to look up the atomic number for copper on your periodic table. It is listed as 29. Copper-62 will emit an alpha particle. So when a nuclide undergoes decay or emission, that particle will appear on the right side of the arrow. So there's our alpha particle, the helium nucleus, with the mass number of 4 and atomic number of 2. So now we're going to figure out the identity of our element by solving for the missing numbers. So we're solving for, remember, A, the mass number, and Z, the atomic number, to figure out the identity of our element X. So let's solve for A. 62 equals 4 plus A. Subtract 4 from both sides. We have A. Let's solve for Z next. 29 equals 2 plus Z. Here's the 29, here's the 2, here's the Z. Okay? Subtract 2 from both sides. Z equals 27. We can use 27, the atomic number, to look up the identity of our daughter nuclide. 27 is the atomic number for cobalt. So this is our alpha decay equation. Now let's try another example. Potassium-40 undergoes beta emission. Potassium-40, the symbol for potassium is K, the 40 is the mass number, that goes up at the top. So use the periodic table to look up the atomic number for potassium. It's 19. Because we're undergoing beta emission, okay, it's going to release a beta particle. We can go ahead and show that symbol of the beta particle after the arrow, and then solve for the missing numbers to determine the identity of the daughter nuclide. So hopefully this is quite simple to look at because the top number is 0 for the beta particles. So the mass number remains 40, mass number remains unchanged. At the bottom though, notice that we have a -1. So let me show you how that would look. 19 equals -1 plus z. Okay, so solve for z. Add 1 to both sides to solve for z. Z is 20. So you would look up the element that has atomic number 20 on the periodic table. And hopefully you're identifying that as calcium. So that's our second nuclear reaction. So if you're in an honors chemistry class, you're also expected to know a positron and electron capture. So positron emission, also emission, note it says emission. So that means that this particle will be released from the nucleus. So it appears on, again, the right side of the arrow. We're given potassium 38, so another isotope of potassium, and that represents the parent nuclide. It releases a positron, which is a positively charged particle. And we're going to use those numbers, the mass number and the atomic number for both of those, to determine the identity of the daughter nuclide. So the top number, you can see we have 38 and 0. So the top number, the A, equals 38. So the top number is going to be 38. The bottom number, we have 19 equals Z plus 1. So to solve for Z, we need to subtract 1 from both sides. So Z equals 18. So use the atomic number 18 to determine the identity of isotope X. Hopefully you were able to see that it was argon. So that completes our positron emission equation. Finally, let's take a look at the electron capture. So we have isotope silver 106 representing the parent nuclide. This is showing an electron capture. So notice the electron appears on the left side of the arrow. It is not being emitted, it is being captured. So it appears on the opposite side of the arrow from the other particles that are involved in nuclear decay. So we are going to use the same process of solving for the missing variables A and Z to determine the identity of our daughter nuclide. Now, remember, for instances when there's an excess of protons, the nucleus will capture an electron from the innermost part of the electron cloud, from an orbital that's closest to the nucleus. And what will happen is that electron will then combine with a proton to form a neutron. So we're going to use these numbers now to solve for the daughter nuclide. So the top number hopefully should be easy to understand. 106 plus 0 is 106. So the the mass number is going to be 106. And the bottom number, 47 minus 1, equals 46. So our daughter nuclide, atomic number 46, that would be palladium. Let's try writing a few more nuclear equations. Mercury 201. So the symbol for mercury is Hg. The mass number given to us is 201 for this isotope. Use your periodic table to look up the atomic number for mercury. It is 80. Now, mercury is going to undergo electron capture. So it's going to capture an electron. That means that the symbol will appear before the arrow. So it's going to capture the electron, and now we're going to have the daughter nuclide as our product. So 201 plus 0 is 201, 201. 80 minus 1 is 79. Use 79, the atomic number, to look up the identity of the daughter nuclide. It is gold. Let's try one more. Americium 243. Am is your symbol, 243 is your mass number. The atomic number for americium is 95. And this radioactive nucleus is going to undergo positron emission. So we're going to go ahead and draw the arrow, and the positron will appear after the arrow. And we're going to solve for the daughter nuclide. The top number, 243 and 0, that is going to remain 243. And then the bottom number, use algebra to solve. So 95 equals 1 plus the bottom number is represented by Z, the atomic number. Subtract 1 from both sides. Z equals 94. So use 94 to look up the identity of your element, Pu for plutonium. And that concludes our lesson on writing nuclear equations.